Okay, so my last video cut out. I'm recording these with my phone, and I got a phone call, and apparently if I get a phone call, it just stops my video in the middle. So sorry about that, but we're going to pick up where we left off. We were looking at this system of equations that we got from the previous page, and again, we have, what we were getting at there was that we have more unknowns in this system than we do equations. All the way back in section 1.2, we had that free variable theorem that says that if this is the case, for a homogeneous linear system at least, then we have to have at least one free variable, meaning we have infinitely many solutions to this system. And it doesn't really take infinitely many solutions to give us the answer we want. We just need to have at least one non-trivial one, but that would immediately follow from that logic. So that's what proves that this is a linearly dependent set. Very useful. Because again, like we said, it gives us a really quick way of checking to see whether certain sets are linearly dependent or not. Now, you don't want to take this theorem too far. You might be tempted to, wrong page. You might be tempted to look at this and say, oh, okay, well, if R is greater than N, then automatically S is linearly dependent. So does that mean that if R is less than or equal to N, then we have linear independence? The answer is no. If R is less than or equal to N, you may have linear dependence or you may have linear independence. It, no pun intended, it depends. So to give you an example, again, the one that we looked at a second ago, this is a set of vectors from R3, and we have a total of 3 vectors. So R in this case would be 3, and N would also be 3. R is not greater than N here, but we still have linear dependence. So don't assume more than you should from that theorem. Okay? Last thing we want to focus on here in this section is going to deal with a vector space that we haven't really done a whole lot with yet. It's the vector space of differentiable functions, in particular n-1 times differentiable functions. Now we're gonna go through this process here, but if you've had differential equations, you have seen the thing that we're going to talk about. Whether or not you were able to get a complete justification for it kind of depends on how it was taught to you. But the tools that we've developed in linear algebra so far will give justification to this. So again, if you've been through differential equations, you're going to recognize this thing. If you haven't, just bear in mind that whenever you do take differential equations, this is going to become something that you use in that class. So try to remember this. We want to focus on the set C n-1 from a negative infinity to infinity. If you remember what this means, this is the set of all functions that are continuously differentiable n-1 times and are defined everywhere. In fact, they're continuously differentiable n-1 times everywhere, is a better way to say that. Basically, for our purposes, that just means we can take any of these functions and take their derivatives n-1 times. The question here is, if I have a total of n functions from this vector space, how can I determine whether they form a linearly independent set or not? And if you think about that just from our definition, that would literally mean that this linear combination being equal to 0, if this set of vectors is linearly independent, would imply that k1 through kn are all equal to 0. But one thing to pay very close attention to is that, again, this thing is not just the scalar 0, it should represent the 0 vector for this vector space. So I have to think of this not as the constant 0, but the constant function 0. And what that means is that this should equal 0 for all possible values of x that I can plug into this. I'll bring that up again when we look at some examples, because it's going to address a really common mistake that people make with this thing that we're going to talk about. Okay, so the goal here is to try and determine if k1 through kn are going to all equal 0, because that would give us linear independence. In general, that's very difficult to do with only one equation to work with, depending on what these functions are. However, because these functions were chosen from this space, C n-1, we can take derivatives. We should use the defining property of this space. If I took derivatives of both sides of this equation n minus 1 times, it's going to generate this system of equations. So here's the original equation that I started with, and here's what happens if I take derivatives of both sides. Notice because it's just a constant times a function for each term, I get the constant times the derivative of that function. And we also know that the derivative of the 0 function is 0. And I continue doing that until I have a total of n equations. This is n equations, not n minus 1, because I have this guy up here also. Okay? But look at this system of equations. What are the unknowns? Well, I have k1s throughout this column, k2s throughout this column. This looks like a system of equations where the k's are the unknowns, and I could write that in matrix form this way. Notice also, because each of these are the 0 function, these are all equal to 0, giving me a homogeneous linear system. So I should start thinking about what tools I have for dealing with this. And what is the goal here anyways? We're trying to determine whether this vector here containing all the k's is the trivial, well, let me say this differently. We're trying to determine if this system has only the trivial solution, which would imply linear independence, because that would mean all of these are 0, or if there are non-trivial solutions. In other words, if one of these k's is non-zero. Well, because it's a homogeneous linear system, and because this is a square matrix, that part's really important. Notice each row has n entries, and each column also has n entries. I can answer that question by looking at the invertibility of this matrix. If this matrix is invertible, then this will only have the trivial solution. If it's not invertible, then it will have non-trivial solutions. That's our equivalence theorem. But also from our equivalence theorem, we know that we can determine whether or not this is invertible by taking its determinant. If the determinant of this matrix is non-zero, then that would also imply that this is only has the trivial solution, which gives us linear independence. If this is if the determinant is 0, we get linear dependence. Okay, so what that matrix here, and specifically its determinant, is very important in determining this question, the answer to this question, linear independence or linear dependence. So we give it a special name. We call that determinant the Wronskian, okay, which is shown right here. So this is the notation your book uses. Other books will actually list all of the functions used in the Wronskian over here somewhere, but we'll use this. So I could state this as a theorem, but we're just sort of reasoning through it right here. If this determinant is equal to 0, then we have linear dependence for that set of functions. If it's non-zero, we have linear independence. So let's use that in an example or two. Okay, I want to start by showing that the set containing just these two functions, x and e to the x, is linearly independent. Now, both of those functions are infinitely differentiable, so they're functions that I could use this with. So we need to construct this Wronskian. W of x equals, okay. Now again, let's come back over here and look at what the Wronskian looks like. My first row is going to contain the functions as is. So x and e to the x. My second row should contain the derivatives of those functions in the same order. So the derivative of x is 1, derivative of e to the x, still e to the x. Okay? This is a determinant, a 2 by 2, so I just multiply x times e to the x and subtract 1 times e to the x, which is just e to the x. Okay? This is not equal to 0. And again, this is another place where I want to point this out. It does not matter if I can find solutions to this equation by setting it equal to 0. There are values of x, and you can probably find them, or at least approximate them, by trying to solve this equation by setting it equal to 0. And that's 100% completely irrelevant to the question that we're trying to ask, because it doesn't matter if there are some values of x that make this equal to 0. What matters is whether or not this is the same thing as the 0 function, meaning 0 for all values of x. Another term that you see used in books that talk about this subject is we say identically 0. This function is not identically 0 because it's not the same thing as the 0 function. So this, being non-zero, means we have linear independence. Okay? Linear independence. Now let's take a look at this next one. Same idea. I have a set of 3 functions, and these 3 functions are also infinitely differentiable everywhere. So this approach using the Wronskian would work. I need to determine whether it's linearly independent or linearly dependent. I can still use the Wronskian, and in fact, I'm going to encourage you to try that on your own. It's going to be a 3x3 determinant, but I want to see if a different approach also works here, just to give you exposure to something else. A good trick to utilize here is trig identities. There's several trig identities I could use, but I do notice here that I have cosine of 2x. And back in trig, you learned about double angle formulas for sine, cosine, tangent. Cosine has 3 double angle formulas. One of them is this one. Cosine of 2x is equal to 2 cosine squared of x minus 1. I believe that's it, yeah. Okay, now notice this cosine of 2x is one of the vectors in this set here. And the other 2 vectors, cosine squared of x and 1, both show up here. What this literally means is that cosine of 2x is a linear combination of the other 2 vectors. It's 2 times one of the vectors plus -1 times the other vector. So based on that other theorem that we talked about, this actually is linearly dependent because we have one vector being written as a linear combination of the other. So this gives me it's linearly dependent. Okay, now the Wronskian in this case, if you were to take that approach, should come out to 0. Notice it's going to take a lot more work to do that because you have to do second derivatives for all 3 of these functions, and you have to do a 3x3 determinant with that. And the end result is going to involve a lot of trig, but the goal will be to show that the result is identically 0. In other words, you should have, if you're left with a big trigonometric expression, you should show, using the techniques and trig identities that you learn about in trigonometry, that simplifies down to 0. But this approach, if you see something like this, you can try that, and that works as well. Okay, so that's going to be it for 4.4.